Good evening, and thanks for joining us. Tonight we'll be discussing how to use creative images to model the real world in your classroom. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. Tonight I'm really excited to be joined by our two panelists, Stuart Moskowitz and John Lemaster. Throughout Stuart's 22 years of teaching math to prospective educators at Butte Community College and Humboldt State University, he's been a leader in bringing professional development to his fellow peers. And as a T-Cube instructor, Stuart coaches educators in the appropriate use of calculators in the classroom and has led over 350 workshops in the U.S. and worldwide. So, Stuart, we're really lucky to have you with us tonight. Thanks for being with us.
Thank you, Mike. It's great to be back again with you.
And John has been a part of the T-Cube family since 1993. He presents annually at conferences, writes math activities, and provides feedback to Texas Instruments on software and products. He teaches mathematics at Purdue University, Fort Wayne, and his passion is to empower students with technology to mathematize the world. John, so great to have you with us tonight.
It's great to be here. Thanks, Mike.
We're expecting a large crowd, so your audio is muted. Feel free to send any questions that you may have for Stuart or John using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, this session is being recorded, and we'll provide a link for the event certificate of attendance at the conclusion of the webinar. We hope you don't have any audio issues tonight, but in the event that you do, try selecting Communicate from the very top of the WebEx menu and choose Audio Broadcast. At this point, Stuart is going to discuss our agenda.
Well, thanks, Mike. Obviously, we are in the middle of our welcome and introductions, and then we're going to move into the idea of modeling the real world, and I want to talk about a little bit about how highway signs are a good use of application of algebra. And then we can even represent things like sea stars on our calculators using just elementary geometry. And we'll do this by learning how to use our own images that we create ourselves, but we'll also look at the ones that come preloaded on your TI-84Cs.
Thanks so much, Stuart. And John is going to discuss our expected outcomes.
Okay, and all those images that you saw that are customs and preloaded, we have provided for you too, so need not worry. After this webinar, you'll see several ways to incorporate mathematics with art and animation, providing wonderful opportunities for student creativity. We'll show you how to use free TI Connect or TI SmartView to create, upload, and store your images, which, along with the pre-installed images, can set the stage for rich experiences with mathematical modeling. Now, we know if you're like us, you'd like to follow along with your calculator. I do. However, this is recorded, and it'll work much better if you wait until you watch the recording to use your calculator. You'll be able then to pause or replay with the recording, and it'll be a much more positive experience. And so sit back and enjoy and watch.
Thanks so much, John. Stuart, you have control. Feel free to share your screen.
All right. Thank you, Mike. So let's see now. Can you see? I think you can see my screen now.
Excellent.
So notice that I have SmartView open on my computer, and I have, as I like to start every class session, I have cleared the memory so that it's only the RAM, so that I'm starting with a machine that should look similar to many of yours right now. So let's start right in. And I want to show you that John mentioned that some of these images come preloaded. So there's a couple ways we can look at the images that are loaded on the TI-84. I'm going to take us straight to the VARs menu, and I'm going to choose number 4, Picture and Background. And right now, we're looking at the PIC files. I want to distinguish between a PIC file, which is a screenshot of the calculator screen, versus a background image, which is something that has been loaded externally. So here are images 1 through 5 are preloaded and come with every TI-84C. So we see the bridge in image 1, we see a slide in image 2, we see a flower, we see a water fountain, and we see a sea star. But I'm not going to start with any of those. I'm going to start with one that I have already loaded myself, image number 6, which is this highway sign. And in a little bit, I'll show you how I take a JPEG file and move it into the calculator. But first, let's go ahead and just use this as is. Now, I have it up here on the screen, but if I want to put it onto the graph screen, I have to go to the Format menu. So I'm going to go Second Format, and I'm going to scroll to the background line, and I'm going to hit the right arrow key, and here's where I can, well, let me just show you first. If we go left, we can scroll through many different background colors. But what I want to do, I don't want to have any color. What I want to do is go through the images, and image 1, 2, 3, 4, 5, and here is my road sign. So let me press graph so we can see that what we've done is we've pasted it right onto the graph screen with the X and Y axis in front of it. And I like to start my algebra classes, and whether it be beginning algebra or intermediate algebra, even pre-calculus, I will often start first day of class with this screen and ask my students what it means. And I will, backing up a little bit, if I ask my students what slope means, I will get many answers, but usually they all have to do with how to calculate slope or just the definition rise over run. Some of the students will remember delta y divided by delta x, or y2 minus y1 divided by x2 minus x1. But what I'm most looking for is, what does slope tell us about the real world? And very few of them can answer it. So let's look at this sign. Here we obviously have a truck on a slope. It doesn't use the word slope, but I think at this point they're understanding that the 7% grade is talking about the slope of the hill in front of us, and they might say that. So I'll say, okay, how steep is this hill? And they'll say 7%. And I'll ask again, so what does that mean, 7%? How steep is 7%? And that's about as far as they can go with this. They don't really know much else to say. So I want to show you this activity, this worksheet that is included in the materials. As John said, everything we're going to do tonight, you can get these materials from the website, and we'll show you how to do that later. So this activity is called How Steep is a 7% Grade, and it starts out with this picture. Question number 1 says, what does it mean? How steep is a 7% grade? And so what my goal here is to get them to make the connection that 7% grade, well, that's the slope, but then we don't teach slope. We don't measure slope typically with percents. But if we can recognize that 7% is just another way of saying 7/100ths, and so we can say, oh, so the slope of this road is 7/100ths. So for every 7 feet we drop, we go 100 feet forward. That's what I want my students to be able to say here. So how steep is that? Is that really steep? Well, I would think that it is steep. Otherwise, they wouldn't put it on a sign. So just how steep is it? So look at this truck. It's on the sign. The truck is on this triangle, on the hypotenuse of a triangle. Is this an accurate representation of 7%? Let's find out. So we'll go back to our calculators, And there's many ways that we can measure the steepness of the hypotenuse of this triangle. I like to use trial and error. I find that trial and error is a way to really focus on the meaning of the parameters in the equation y equals mx plus b. And I'm going to start with the easiest linear equation I can think of, which is simply y equals x, and I'll press graph. So we have y equals 1x plus 0. We have a y-intercept of 0. We have a slope of 1. And we can see just by inspection that this blue line is steeper than the hypotenuse of this triangle. So if I want to what I'd like to do now is manipulate this line and get it to be parallel to the slope of this, the hypotenuse of this triangle. So since the blue line is steeper than the hypotenuse, okay, I need to change this equation by making the slope less than 1. This is what I want my students, of course, to answer. So again, trial and error. Let's try 1/2. And of course, I'm going to go alpha F1 and choose my fraction template. And so I'm going to put 1/2. Let's see if 1/2 makes a good one. Again, trial and error. Ooh, well, that's a whole lot closer. Looks like it might be still a little too steep. Can I go a little bit? Can I adjust it a little more? Let's go back to y equals. What if I said 1/4? What if I said 1/4? Would that be better? Well, that looks like that's probably not steep enough. So I'm going to go back to y equals, and having done this before, I use trial and error, and I find out I'm going to stick with I'm going to go with approximately 4/10. Of course, I could type 2/5. I could type 0.4. Many different ways I could type it. And let's see if 4/10. Oh, that's looking like it might be parallel. Wouldn't it be nice if we could shift this line up? And what a wonderful way to introduce transformations of functions. Okay, I want to shift this blue line up so that it's superimposed on top of this hypotenuse. So how do I do that? Well, let's go back to y equals mx plus b. And right now, b is 0. If I want to shift it up, I need to add a constant. So how about if we add 5? And I'll press graph. And, there's something that I forgot to do. And I got to come back here. And much of what I've done here is made an assumption that I can't make. And this is actually, sometimes they'll say every mistake I make, I'm going to do it on purpose. I'm looking at slopes, but I'm not looking at a window that's square. My aspect ratio is not 1:1. If I'm in the default window, -10 to 10, negative y's are going from -10, and that means because it's a rectangular window that my x's these tick marks are spread out farther than these tick marks. If I want a slope of 1 to actually be equivalent to a 45-degree angle, then I better go and make a square window. So I'm going to go to zoom, and I'm going to choose zoom decimal, which is a quick way to get there. And of course, I added 5 to it, which takes me off the screen. So I better come back. Let's try adding 2 instead. Oh, much better, but it looks like I better come down a little farther. So I'm going to. I'll change it. I think when I did this prior, I used 1 2/10. And look at that. We have a pretty good fit. Of course, this isn't exact, and the intention here is not to get an exact fit. Of course, and so there are multiple correct answers for this. The idea is, I see that this blue line has got about a 40% slope, 4/10. That means this truck is on a hill that's got a 40% grade, not a 7% grade. Well, wow, this truck is much steeper. Why didn't they just put a scale drawing on it? So what does a 7% slope look like? Well, that's easy enough. Let's go back to y equals. Let's let y2 be 7%, and I can type 7/11700, or again, just to to show that we can do this many different ways, here is another way of typing 7%. And I'm going to press graph. And we see now a red line that's got a 7% slope. But that doesn't look very steep at all. Well, have you ever tried to ride a bicycle up a hill that's on a 7% grade? And I challenge you, especially if it's 3 miles long, I challenge you to ride up that hill and then tell me it wasn't a steep hill. 7% is a steep grade. But then it's hard for us to make the connection between steepness and percent. So wouldn't it be nice if we could convert this to degrees? What's the angle of inclination of a 7% grade? Well, what a great way to introduce trigonometry, because the inverse tangent of 7/100ths will give me the angle of inclination. Let's try that. Let's go back. So this is since tangent, just a quick little review. Since tangent is the ratio of the side opposite divided by the side adjacent, that gives me the rise divided by the run. So the tangent gives me the slope of the line. So the inverse tangent, let me go and get inverse tangent of 7/100ths. And again, just to see the difference, I can type it as a division statement. There's many ways to type 7/100ths. And I see, and I get, 7/100ths gives me about 7/100ths. That's hardly anything at all. Are we talking about 7/100ths degrees? And this is where I want my students always, always, always to ask if the answers that are coming out of the calculator, do they make sense? Calculators never make mistakes, but we make mistakes all the time. And to say that this is 7/100ths of a degree, wow, that's nothing. But look up here. We're in radian mode. And I like the TI-84C and CE because they give us these mode settings right on the home screen. Let's go to mode and change it to degrees. Don't forget to say please by pressing enter. I'll go back to the home screen, and I'm just going to press enter again, and now it reevaluates the inverse tangent of 7/100ths, and we get about 4 degrees. Still not very much, but at least 4 degrees and is something noticeable. 7/100ths of a degree, I don't think we would have even seen it. Would have looked like a horizontal line probably. So we see that this red line, a 7% grade, is only an angle of 4 degrees, but it's steep enough that they want to put the sign there. So now we can go out and find the slopes of, you can take any image you want and paste it on, and then use this method to find the slopes and the lines of any image that you choose. So this is one example of finding a real-world application and then using beginning algebra to model what we're trying to understand about this, in this case, a highway sign. So I want to show you one more example before I pass the baton to John. And the second example I want to share with you is the sea stars. And the sea stars that I want to use, well, let me go back here and show you that if we go back here to format, and let's go to image, the background image, and go back to image 5, here's a sea star. But my goal today is to try to draw a star polygon that will be close to this particular sea star. And I could do it with this one, but because it's so asymmetrical, it won't be much of a fit. So I went onto the internet and I started looking for my own sea stars. And I did find one. And I found one that I was quite pleased with. Let me show you what it looks like very quickly. Just a JPEG file of it. Here it is. Okay, and so what I want to do is take this JPEG file and get it into the calculator. And I want to show you just how easy it is. And it's just as easy with the handheld as it is with SmartView. I'm going to go to the little magnifier, which will open up my directory. And I can also do this with, if I have a handheld plugged into my computer, I can use TI Connect and get a very similar directory. Now I'm going to go and I'm going to grab this image and I'm going to drag it into the directory and just let go. And notice that's all it takes. Notice that there was an image called C*5. It's a JPEG file. And it's asking me, where do I want to store it? And I don't want to store it as image 1 because I have another image 1. I'm going to store it as image 7. And I'm going to hit send. And that's it. There it is. And you'll notice here it's been added to my directory. If I go back to the calculator screen, I can now go back to format and go to background, and I'm going to choose image 7, and I'm going to, well, let's see, I'm going to go to y equals and press clear. We don't need to have these linear equations anymore, and I'm going to go back to graph. I'm still in my zoom decimal window. And my goal here is I'd like to see if I can draw a star polygon on top of this C*. And I'm going to let the C* help me to draw the star polygon. And I want to draw a 5-pointed star polygon. I'm going to start with a little review of polar graphing. And as I said, polar graphing is something that I never really studied till I was well into the calculus sequence back when I was a student many, many years ago. But once I saw how powerful the TI technology is and what I can do with polar equations and when I'm in polar mode, I thought, wow, I can actually do some elementary geometry with polar graphs. And let me show you what I'm talking about. I'm going to go to mode. I'm going to leave it in degree mode, and I'm going to change it from function to polar. So I'm now in polar. Don't forget to press enter. Say please by pressing enter. And now, again, I go back to the graph screen. Nothing looks different. But when I go to y equals, instead of y equals, I get r equals. R stands for radius. So let's look at something here. Let's just type r equals 4. And let's see what we get. Now, when I press graph, I'm not going to get much of anything. There's just this little tiny blue line here. And that's because if I press trace, we see we start out right at 4, 0. And then if I hit the right arrow key, theta jumps to 1300ths, and then it keeps jumping up. The problem here is that the default setting is for radians. So what I have to do is go to zoom. I'm going to change it to zoom standard. Well, here, let me show you what radians is. Notice when I'm in when I take the default settings, even though it says degree mode, when I switch to when I switch to polar graphing, not only do I have X min and X max, Y min and Y max, but I now have theta minimum, maximum, and theta step. Notice that theta is going from 0 to 6.28. That's 2 pi. That's one rotation around the circle, 2 pi radians, in increments of 1300ths radians at a time. We won't get into where this came from. As I said, when I'm doing this with younger kids, I'm just going to stay in degree mode. So I'm going to go zoom standard. And all of a sudden, I now have an ellipse, not a circle. So what's going on here? Let's go to window. Notice that we're back in the default window, -10 to 10, -10 to 10. Remember, I did a zoom standard. And now theta is going from 0 to 360 degrees in increments of 7.5 degrees. So let's do zoom one more time, and let's change it to that square window, zoom decimal. And now I have what appears to be the C* inscribed in a circle with radius 4. If I press trace, r equals 4. My radius in my circle is 4. And if I hit the right arrow key, we're now moving from point to point. The calculator is plotting points in increments of 7.5 degrees. And of course, since r equals 4, the radius will always be 4. Notice it's giving me rectangular coordinates. And I can go around the circle. And so really what I'm getting is a polygon, and it's connecting the dots. Is what it's doing. It's plotting a point every 7.5 degrees, and it's connecting the dots. So the first time I saw this, I thought, well, if the default is 7.5 degrees, what would happen if, would I get a better circle if I plotted a point, say, every degree? Let's see. Theta step equals 1. And notice I do get slightly better resolution because I'm plotting 360 points instead of whatever 360 divided by 7.5 would get me. I've quite not missed any points. Well, this is a great circle, but my interest is in star polygons, and this is where I believe, as long as my students know that there's 360 degrees in a circle, watch what we can do. So I'm going to go back to Window, and instead of plotting a point every degree, I want to plot just 5 points around the circle. I want a pentagon. Since I'm looking at a 5-pointed C star, I would like to do a pentagon. So if I was to plot points, if I only wanted to put 5 points around the circle, then what I want is the step to be 1/5 of 360 degrees. Now I know that 1/5 of 360 degrees, I can do this computation, but I want you to see that the TI-84 can do the computation for you. 1/5 of 360 degrees means we're going to plot a point every 72 degrees, and we're going to connect the dots. And look at that. We get a pentagon. Gee, it's starting to get a little harder to see it just because we have some blue on blue. So I'm going to go to Y equals, and I'm going to take advantage of graph styles. And I'm going to change blue to, how about magenta? That might be a little more contrast. Let's see if we get enough contrast with the magenta one. I can see that better. And I get pentagon. Wouldn't it be nice if we could get the vertices of the pentagon to match the vertices of the C star? Let's see, maybe 30, 40 degrees. If we could move this point right up to here, let's see. Let's start it at, say, 40 degrees. Ooh, that's just a little too far. So let's back it up. Let's try 30 degrees. So now I get a point right here. My points match. But then why didn't it close? It didn't close the pentagon. Well, let me press trace. And we see we get a point at 30 degrees. And then we add 72. We add 72. We keep adding 72. We get to 318. But to complete the pentagon, we would have to add 72 to the 318. But our theta max is only 360. So how about if we change, since we changed theta minimum to 30, how about if we change theta max to 390 and we get our pentagon? So we're almost there. I want a star polygon. I see that if I go from the 72, I can connect consecutive adjacent vertices. But I want to go from this point straight across to here. I want to skip this one. So instead of going 72 degrees, I want to double that to 144 degrees. So I'm going to go back to Window. I'm going to change 72. I want to double that, I said. So I'm going to let the TI-84 do the computation for me. There it is, 144 degrees. I press graph, and I've got 1, 2, 3. But in order to get the last 2, I need to continue on. I went around the circle. Trace, I got up to 318 very, very quickly. So let's go back to Window, and let's go around the circle again. Let's add 360 degrees. Let's go around the circle twice. And of course, whoops, I'm going to add that. It does the computation, and there it is, my 5-pointed star. Very, very quickly, since I do want to make sure we have time for others, is that, let's take a quick look at the 11-sided C star. Very quick look at it. So I'm going to go back to the directory just to run through the steps again so that you can see it again. I'm going to take a JPEG of an 11-sided C star and drop it in the directory. I'm going to change it to image 8. so that I don't lose any of the existing images. Of course, I can have more than 10 images if I just save them on my computer. Let's send this as image 8, but I can have 10 on there at once. And I'll go back to the calculator. I'll go to Format. I'm going to change image 7 to image 8. So go back to Graph. Now I have an 11-sided C-star. So I'm going to do this relatively quickly because I'm watching the clock. And instead of going to what I want to do now here is I want to get 11 points around the circle. So I'm going to go back to Window, and I want my theta step to be 1/11 of 360. Of course, that's not a very pretty number, but the calculator doesn't care. And I now get vertices that come pretty close to matching. Of course, the C-star is not perfectly symmetrical. And in order to get with 11 points, now I don't want to go to every second one to try to match this. I want to go from this one, I want to go across to here, and then across to here, and then up to here, and then down to here. I want to go to every fifth one, not every second one or every third one. There's actually many star polygons I could do with this. So I'm going to go to Window, and I'm going to go back to Theta Step, and I want to take 1/11, but then I want to multiply that times 5. So I'm actually taking 5/11 of 360. And again, the numbers we get are pretty ugly, but notice now that we jumped from here to here, and we didn't go around enough times. So let's go around the circle 5 times. 360 times 5, but we did a little shift of 30 degrees, so I'm going to add that 30 degrees back in, and I'm going to press Graph, and I get an 11-sided star polygon. It's not an exact match, but we get to use a C-star as a model. So that's enough for polar graphing for now, and C-stars to be modeled with star polygons. I'm going to turn it over to you, John, to hear what else can we do.
Stuart, that's really awesome. Thank you. I love how also with the calculator, students get to explore and say, oh, wait a minute, I'm in radians, I should be in degrees. And they learn it so much faster if they take the wrong turn, and even though it doesn't feel so good, I mean, I really appreciate when we take those opportunities and say, hey, that's a window into thinking, as opposed to, oh, you did it not the way I wanted you to, you know. So I think the opportunity that the calculator can take our ideas in the curriculum and bring polar right into elementary is really a cool approach. One of the things that you mentioned about the loading of the images, I wanted to also connect again a little that there's a few tips that we could offer, and those are also in your associated documents that you're going to get. So if you ever have an image that has an extension, and if you've done anything with an image, you might notice, I'm going to throw a folder on the screen to show, here's an image of our school mascot, and one of them's a JPEG and one of them's a PNG, and this is our school logo, and you can't see very well, but this is really supposed to be transparent if I were to land this on. So these can be dragged over, and I didn't include these in your file because they're our school, but what's nice about it is to know that either of these formats or other formats like TIFF or GIF can be put in your calculator. And what's counterintuitive to me that I wanted to share with you that you might also say that's a surprise is that sometimes people think higher resolution means a better result. And actually, I could have two images that have the same one's really high in resolution and one is not. And when you drag them over, they go through the meat grinder and they turn out to be the same piece of sausage. And it doesn't matter whether it's a high resolution or low resolution. So it really doesn't make a difference. What does make a difference is the appearance of the image. And that's maybe something that can be helpful if you're using custom images. So if you were to put a painting of Matisse, which has pointillistic, impressionistic dots all over it, or a Jackson Pollock artwork and throw it in, you would not get a very good result compared to something with a lot of solid colors, clear boundaries, like this logo, for example. And so that's important. Try to get something that's a little bit more, has a lot of solid in it. I'll just share with you the looking of that, and it's another way to also show a different way to get the images. You mentioned the format menu as well as the variables menu. If we go to the draw menu, there's an area here called background, and I found myself to be very careful not calling an image a picture, since that's also a different meaning to TI world. A pic variable is something you would have used commands like these to draw on the screen, but the image is really in the background. And here you can have background on or background off, very handy tools. Now, if I hit background on, what happens is I plaster it on the home screen. That's one way to get an image, and then I could put its number. But let me share with you a different way to do that. And I'm going to go to the graph screen and share with you, that's my image. And it doesn't really look that bad. And I could do things with artwork in the classroom to mathematize things. So one of the things that can be helpful is when mixing math and art is, like you shared with Stuart, the road sign, is say I want to know what angle this meets. So we could model a slope of a line here and find the line that is of opposite slope over here and find then the inverse tangent of that slope and then get an angle by subtraction. So there's lots of creative stuff. I don't want to go into that because that you kind of did already. But you also, just a reminder, we are in a window that is a square window. So the tick marks that are the same units apart look the same units apart. Lines that are perpendicular look perpendicular. Lines that circles look like circles. So that's really important if you're doing mathematizing artwork. And the other thing that I would like to share with you is I'm now from the graph screen. So here's the graph screen. And when I go to second draw and do what I did earlier, there is the background on. Last time I pressed it, I didn't come from the graph screen, and I pressed this and I got on it just plastered the command on the home screen. But now look what happens. It's interactive. And I can scroll through the images. So image 0 is actually one of my, it's actually the JPEG right there. And the image, if I use the left or right arrow, I can go back through the images. Now, image 9, that is actually the ping image that happened to have transparency. Transparency does not move over when it goes through the sausage grinder, and so you may not like that result. It also is very interesting to note that if I pressed enter, by the way, that's another way to select the image. I press enter and say, please, it'll slap it on there. You might notice here that this is the shape of the TI window. And it's written here, proportional to 83 by 133. And in the documents, we've got some tips written there. But here is the image that is, I just have it in Paint. I took something that was proportional to 183 times 133 by 133, and then I dropped the image in it and tried to center it. And you you don't need to do that, but if you wanted it to have more control, that's another way you could do it. And so part of what I want to hope tonight as we leave with is, how do I control what I want to do? And that's one way to do that. And actually, when we looked at the idea of slope and the tangent and the inverse tangent, I found it very interesting to talk to my colleagues who teach graphic art, that they're using the inverse tangent all the time with their students when they're using Photoshop, because they're looking at pixels and finding calculations and then needing what to rotate. Here's just a moment now. If there's any questions, Mike, do you see any questions that people have about images or anything, just to make sure that those details are...
Sure. At this point, John, I don't see any, so far so good.
Okay, great. And please know we have provided our contact information. If you try something, that you can do that, and it will. You can always contact us. This is the document, by the way, that has all the details in here about images. So and cables and so forth, and 83 by 133. So you'll get that later. And there's some other things I want to share with you that you'll see, and that is this document will be coming to you, and it has some links in it where we used the preloaded images in other activities. And one happened to be one I did just recently in October with Karen Camp, and I did this bridge. And I started with the bridge, and we used function mode to find, let's get the bridge on here. I'm going to quit and share with you that, remember when I put that background up there? If I just change the bridge, if I know it's background 1, that's another way I can get the bridge on. And there's my bridge. So there were 3 ways I can get an image. The second, format, I can go and paste in the command with the number of the image, or I can go from the graph screen to second draw and then select it off of a buffet. And okay, so Karen and I played with images a little, and we found in function mode a line that would take a boat and put it down the river. And we put a line here that would make a train cross the bridge. And here, this is actually, again, we're using a zoom 4 or a decimal window for purposes which are it makes the numbers friendlier when I trace on them. And if I were to put a line y equal 1 1/10 on there, it would be very nice and make the train. So what I'd like to do is show with you how to use parametric mode. And if you want function mode, see the other webinar. But I wanted to take this and extend it because you can do it both. And I will tell you, I've used parametric sometimes without my students doing it, just to animate some mathematics. And so it's really fun to share with you, just as you shared, Stuart, with Polar. And if I also want to do animation on images, this is very, very helpful to put on simultaneous. If I have more than one graph being animated, simultaneous will make the movie work much better. So simultaneous, we're going to be in parametric. And when I press parametric, you might have fun noticing there's something similar to the Polar screen. These numbers kind of work really nicely. But that's great if you're doing a circle. We're going to animate a train going across a bridge. So I want the train to go from -6.6 to +6.6. Why I do that, I'm going to go by 0.1s, just arbitrary there, is that I want the T min-max to match the X min-max, because this is now controlling the graphing increment. And that's the key that is different about parametric than in function mode. if you remember, in function mode, there was a little delta x down here at the bottom that would talk about what's the pixel gap between each plotted point. Now that's controlled by the t step, and I can make it fast or slow, and it gets a lot of power. So if okay, here's the cool part. If I stick a t in here, by the way, x now, the xt theta n button is a t, and 1 1/10 here, this will graph the line y equal 1 1/10 for x, the horizontal, to go from t equals -6 and 6/10 to +6 and 6/10. And let's see it go. Oh, and I already have it, so that's a cute animated path. And we press graph, and here comes my train. Now, I certainly could do that in function mode, but I got a lot more opportunity for creativity now with down here this bridge, this river. And if I were to look at right here, you can see about a -1 y-intercept would be a line going of positive slope. Let's go down 1 and over 2. I could certainly put a grid in there, but a line of slope 1/2 that has a y-intercept of -1 would be a nice path for a boat. So let's put that in there and see how parametric really can enjoy some new power here. I would like, and this is also fun, if I notice there is no green word or letter icon on this button, but because the calculator was made after this feature was done, and you may not know this, but if you, makes my evening. If I press alpha x, I get this stacked fraction. Now, by the way, you can also get it in the F1 menu, alpha F1, and there it is hiding there too. But I'll press clear out of there. I'm going to stick a half in, and I need to ask it to draw that line. Now, keep in mind that we're just really doing substitution. When x is t, this is the graph of y equals 1/2 x minus 1. And it's going to go from -6.6 to +6.6, which you may think, now, if I just press graph, by the way, it will graph afterwards. I'm going to not want that. I want the simultaneous. So here's my other best friend on my calculator. I'm going to press on to stop it. Enter paused, on stops. And see, no more dialing up there. And I'm going to go second quit. And I love this button. Second draw, number 1, clear draw. It's an easy way to replay anything on the screen. And if you're going to do animation, this is a nice button. And now it wipes everything off and refreshes the calculator. And here comes my simultaneous. Now, I love this, but something happens that you may not like, and that is the boat doesn't stop, and it turns into chitty chitty bang bang and it'll hit the train, and it'll be, just a newsreel. So we need to change this, and here comes creativity. Wouldn't it be great if I could have the boat go toward the horizontal component to go from -6.6 all the way to 0 and then backwards and reverse? Well, what could do that but an upside-down parabola? And if we look at a upside-down parabola, something like that, this could go from -6.6 to +6.6. That looks just like a -t². Well, let's enjoy that. I'm going to press on, and I'm going to change him to -t². But I need substitution to happen, so I'm going to hop on top of my t. For fun, I'll stick second insert in, and now I will make that squared. I have to be careful, because what I want to do is make sure this actually turns into y equals 1/2 x minus 1. And so if I put the negative t squared in where the t used to be, the graph will be equivalent to the path of y equal 1/2 x minus 1. And I had interrupted the graph, and so I think it'll just start again. If the graph already completes, I can need the clear draw. And here it comes. Now, you're right saying, where's the boat? And I just like to point out that the boat happened to do a little bit of stuff off screen. You see, remember that is graphing off screen. And lots of things can happen here, which you might now, if you wish, you can change things to kind of liven things up. One thing is we can speed up the train if we wanted to by making it go twice as fast. So when I do that, now the train is twice as fast, and they're kind of connected together. So I have opportunities for students to play. The other thing I can do is, did you notice this is still going? Because it goes all the way to 6.6. But if I decided to half it, and that's fun, let's divide it by 2, again, just to show that we can do what we did earlier. Now, things might look a little nicer, because negative 3.3 to positive 3.3 would actually have most of the graph appearing onto the stage. Here we go. And there she is. So governing the Tmin and Tmax controls a lot, as well as your equations itself. And I find myself always asking questions about how does this help me teach better. And one of the things that my students have to do in pre-calculus is they have to eliminate the parameter. You've seen if they've done pre-calc these kind of questions. And I load up, first of all, a lot of stuff that's really easy. Like 9t plus 9, when they replace these, this is y equals 17 cosine x minus 3. So you can see that I've rigged these to be very nice and easy. It's a substitution. And there's another part of this handout where I ask to restrict the domain, so we see that these aren't the same if I substitute without looking at domains. And so some excitement happens here. And you'll notice that is exactly what we're doing here, only we're getting some power to it. Now, what's fun is I can add more boats, I can do more with my train motion, and I have something that is nice on the smart view that helps me very much as a teacher, as well as doing webinars, and that is, and I've loaded all of these in your associated documents that you're going to get. When you go to the file that you want of the, let's share with you here, there are little states, they're called emulator states, that are simply just a calculator. This is shares with you everything I have. So here are 5 emulator states. That's like handing you 5 TI-84CEs. So you have more than 10 images. I have 10 images for every one of these calculators. I can store unlimited number of images on my computer, and it's just a riot. So I'm going to load. Oh, did you notice? I can make the state name or the image name anything I want. And so it's nice to help myself out and change those names when you store things. All right, now let's load it. And I'm going to load. And what I'd like to do is go to the bridge folder to share with you that. And I have 2 boats now. It'll ask me, are you sure? And here she comes. And I put some clear draws on the home screen just for fun to make sure that it's easy. And now, this boat looks and sees, oh, he's coming at me. Oh, no, they're going to race each other. I better speed up. So the magenta boat really, really has to move fast. And so I've made a little drama. So I could ask my students, what do you think I changed on my screen to make that occur? And by the way, there it is. Let's go to the y equal. It's in fact an exponential. If I stick an exponential in, now the horizontal component is actually going by an exponential, and rather than a parabola. And so you can really do some fun stuff in here. And I'm in radians if I did this is where I would turn the students loose and empower them. And if I stick a cosine in there, now it can go back and forth. And I can now, as we said earlier, it'll set the stage for modeling. I might ask, okay, what would make that train, what's another way to make that train go forward and backward that isn't a cosine? And they may say, they'll probably say an upside-down parabola. So then I have to say, okay, well, it starts at negative 3.3, and so it is a parabola that has to look like, I just undid something. It has to look like this, where the t at negative 3.3 is negative 6.6. It goes all the way to 6.6 when t equals 0. So this is t versus x versus t. And they can mathematize that parabola, and they can get a formula for it. And here we'll just load it. It's a little uglier, but fractions are people too, right? So here we go. There she is. Let's get there and clear draw. And it's kind of fun to see how slow she gets compared to the inverse cosine. And what you might wonder is, why is that different? And look at the parabola versus the upside down, the cosine, this is regular cosine, and that it's slower rate of change here near the border than the other one, and that shows in the graph. And if I ever, had more time, I'd put a tangent on there and slap it in there. So there's a lot we can do. And I know that, Mike, we have to close. But what I want you to notice is when you go back to the documents, you will see a lot of opportunity for you to play with by just loading some of those emulator states and seeing what went on. So I did more with the slide, and then every other activity has a folder. Every other image has a folder. So lots to do with parametric. Even if you're in Algebra 1, you can do fun stuff on the slide. I have a bug going down and a Mary Poppins bug going up the banister. All sorts of fun. Mike, it's yours to wrap us up.
Thanks so much, John. We're really excited that the T-Cubed International Conference is coming in just a few short weeks to Baltimore, early March. It's really a great way to learn more about some of the new technology that TI has been putting into classrooms, as well as current technology that we've had for a long time, and what may be changing with it. So please feel free to visit us at the T-Cubed International Conference. We really hope to see you there. Please feel free to visit our website to learn more.
Can I throw a shameless plug in? That
Please.
Stuart and I are going to do an image presentation there where we're going to actually deep dive into it.
That'll be exciting.
Yeah, we'll have fun. Thanks.
Thanks for mentioning that, John.
To receive a certificate of attendance for tonight, go ahead and click that link in the chat window. Also listed is a link for the documents that were used tonight by John and Stuart, and as I believe both of them mentioned, they spent a lot of time on these documents that they're giving you, so please feel free to look through that. All the images are included, as well as lots of other goodies. So again, links for the certificate and the documents are listed in the chat window. And if they're not working for one reason or another tonight, hang tight. You'll automatically get a follow-up email in a couple of days. And in that follow-up email will be a link to the recording from tonight. a link to the certificate, and a link for the documents as well. And if you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. Thanks so much, Stuart and John, for everything you shared tonight. I really appreciate it.
Thank you,
Great.
Mike, for putting all this together again.
Yeah.
Nice working with you.
And thanks, everyone, for coming.
Likewise. Thank you, everybody.
I agree. Hope to see you back online real soon. Have a great night.